So today we're very happy to have Jiapeng Zhang visiting us from University of Southern California, where he's an assistant professor. Jiapeng got his PhD from UC San Diego with Shanghai Lovet, and after that he did a postdoc at Harvard. He's an expert in Boolean function analysis, computational complexity, and more recently learning theory and cryptography. He won Stock 2020 Best Paper Award for improving the sunflower lemma, which is not what he's going to tell you today. But feel free to ask him about that offline. With that, I'll give you the Jiapeng.
Okay, thanks for this introduction. We're happy to hear, and thanks everyone for attending. Okay, so today I will talk about sublinear proofs over polynomial rings. Yeah, this title looks like very complexity based. Actually, this is what I tried to do. So because I always try to give complexity based talks, but actually these things are very related to cryptography and some other things such as blockchain. I'm sure if I advertise it as a blockchain, there should be more attendees. But I try to in a complexity theory way. Okay, so let me get started. Okay, so in this talk I will go through 4 parts. So I will try to maintain in a very high level way so that everybody can follow. So the first part I will going to tell you what are succinct proofs, and then I will talk about polynomial interactive oracle proofs, and then some check over polynomial rings, and also then some summaries. Okay, so let's get started. I will first try to recap some definitions. So because we are talking about succinct proofs, so then the first question is what are proofs, right? So the proofs here we are talking about NP proofs, for example. So NP proof. So this is a very this is a copy and paste from my lecture notes from the computational complexity. So what are NP problems? Okay, so NP a language L is in NP if there exists polynomial time algorithm A started for every input. So if X is a yes instance, then we have a witness to verify this is correct. If it is not a yes instance, so then basically then there's no way such that you can convince the algorithm A to accept it. Okay, so this is I think this is pretty standard. Okay, so this is the proof we're talking about today. Okay, so actually this is the definition. Actually, you can imagine in an alternative way. It's just like a communication between 2 parties. So the party is given any statement. So there's one person who we call it a prover. We prover want to convince you that X is correct, and also there's a verifier, such that we want to the prover want to convince the verifier that the statement is correct. Okay, so the process is that if this is real correct, so then the prover has a chance to convince the verifier. If this is not correct, then the verifier can always identify this is not correct. Okay, so there's no way to cheat. So this is the NP problems. Okay, so by the way, if I have any question, feel free to stop me. Okay. Yeah.
So this is that you know witness, right?
Sorry, the prover knows the witness. Prover knows the proof, but the verifier does not know the proof. So imagine that I want to claim that I know how to prove P is not equal to NP, or some famous mathematic conjectures. So now you are the verifier, you are the reviewer, and I am the prover. So now I want to convince you this is correct, right? So if I just show you the proof, because if you have mathematical background, you can check line by line. Okay, so this is correct. So the thing is that the statement is that you're the verifier. I don't know whether I'm correct or not. Probably I cheat you, right? I don't have a proof, but I claim I have a proof. So this is the I have the W is the proof, and the statement is X. The statement you can imagine is just like a famous mathematical conjecture, and the proof is my proof. Okay, so actually, so now this is the NP definition in the previous slides. It's just the 2-round proof. It's okay. I send you the proof directly, and you verify it, right? So this is a very intuitive way. Okay, so but there are several problems here. Is that so? There are 2 drawbacks I want to mention. Is that in this communication, in this prover's process, so first the verifier gains the knowledge of W. So for example, if I want to, so there's a found problem which proposed by NDL in a couple of decades ago. It's just I want to prove you that I'm billionary. Of course, the most straightforward way is I show you a bank account. Of course, you believe it. But the problem is that I don't want you to know how much I have. I just want to convince you I'm a billionaire, right? Of course, I'm not a billionaire, right? Okay, so this is the case that the verifier sometimes against the knowledge of W. But in many cases, so the prover wants the knowledge of W, the prover have some sensitive information we want to preserve. So in such a case, we do not hope the verified to know the knowledge of the W many times. Okay, so this is one thing, is one drawback. So the second drawback is the length of the proof is really, really large. So imagine that there are some mathematical conjecture which is called the ABC conjecture. And the author of this paper still believe the correctness of proof, but nobody can verify it yet. So that doesn't happen because the proof is too large. It's really, really long. It could be 100 or 200 pages of mathematical proof. Nobody can follow it. So the proof is really long. So there are two drawbacks of this type of communication. Okay, so yeah. So this is why we motivated to the next question is that, okay, so then how could we modify this process? So this is something called a very interesting thing in complexity theory, which is called the interactive proof. The interactive proof is that instead of sending the knowledge directly, so this is the communication between two parties, the prover and the verifier, they can communicate to each other. So I first show you something, right? And so you say, okay, then I have some question about your proof. Then I ask, where is my question? And then we have a communication. You can imagine this is the process. This is called interactive proof. So we say this is, but the interactive proof, we also consider probabilistic interactive because randomness is allowed between these two parties. So we say this is, we say a language L has an interactive proof. If there exists a polynomial time, this is probabilistic. This means probabilistic polynomial time algorithm P, such that the prover and for every x, if x, the completeness means if x is indeed correct, so then the prover can convince the verifier to accept. It's high probability. But the soundness means if this is not in L, then the prover has no way to cheat verifier. So the verifier can detect that this is incorrect. Okay, so if you go back to the previous slides, so that is also a one round interactive proof, right? So I just send the witness W directly. Yeah. Okay, so then the funny thing, the interesting thing here is that if we allow interactive, could we do something non-trivial that is faster than what we question?
The randomness here is only over the verifiers.
It could be both. It doesn't matter. Yeah. Okay, so some of the desired properties, as we mentioned, we want some nice properties from the interactive proofs. So one is the public coin. So the public coin means the verifier only send uniformly random bits. So I usually just send uniformly random bits. This is called public coin. Okay.
Oh, sorry. What is that? I'm assuming the prover doesn't know the verifier's randomness.
Yeah, beforehand. Yeah. The prover will see it after received it from the prover. Yeah, but this is always uniformly random.
So I guess it's a public unpredictable.
Yeah, unpredictable. Yeah, prover. Yeah, because it's the prover does not know it. So that is how we prevent the prover to cheat, because you never know the randomness before. Yeah. So public coin. Yeah. And the zero knowledge is a very useful thing. And so this captures the first drawback is that the prover does not reveal any information from W. So this is just a very informal way to explain for it, but we will have a formal definition for it, but I'm not going to touch this side for now. So the succinctness, the third property of the succinctness is that the communication cost is much smaller than the size of W. So we hope this to be much smaller. So that's why we call it succinct proof. Succinct proof is very useful as well. Okay, so by the way, why we need a public coin? Because whenever this is an interactive proof, right? So, but in cryptography, there is a heuristical transformation which is called Fiat-Shamir transform. This is something usually convert public coin interactive proof into a non-interactive proof. So because in many applications, such as blockchain, for example, they want non-interactive proof. What is non-interactive? Non-interactive, the prover still just send one message to the verifier. So this is called a non-interactive proof. So yeah, so in cryptography, so basically this is a heuristic to transfer any interactive proof by using a cryptographic hash function to do this transformation. But in a cryptographic hash function, they have a way to convert any public key and interactive proof in number. Okay. So yeah, any question so far? Okay, good. Okay, so let me give you an application of the succinct proofs. So why we need succinct proof? This is one application that is very useful, particularly in blockchain. So yeah, so this is how to aggregate signature. So for example, digital signature is a very important property in cryptography. Actually, digital signature happens everywhere in our daily life. So what is a digital signature? Digital signature is that you have a message M1. And there's a one party. So for example, you want to sign the message, you have some secret key. So proving that is you. And then you can prove using secret key to sign M to get a signature M1, a sigma 1. And so this is another public key. Public key is that everybody else has to do with public key. So whenever I have this public key that associated with use private key, and I have this message, and I have this thing, then any people from the public can verify, okay, so this message, this signature is indeed signed by you with the associated with this message M. So, okay, so then, okay, so imagine that there are many people, a lot of people in this room, right? So everybody signed a signature. Sign the signature, so we want to aggregate that. So when we aggregate it, so we just combine everybody's signature into a whole signature. So that so whenever in future people can check the whole all of the signature together. So without individually check everybody's signature, we just combine or aggregate all the signatures together. Okay, so why this is particularly useful in blockchain is that because in blockchain there are so many signatures. So if you can combine them, you can aggregate them, so then you can put all of the information into a small space. Okay, so the question is how could we aggregate them into a short signature? Okay, so without considering the short signature, so what is the naive way to aggregate that? Without the shortness, what is naive? It's too advanced. Just concatenate, yeah, this is the most naive. Just concatenate without, yeah, this one I already give the hint is without considering. Yeah. Just concatenate that. Yeah. Okay. So actually, you can imagine the concatenate of the witness of seeing these signatures, right? So the aggregator is the proof right now. The aggregator see this message signatures, and I want to prove a verifier that I have seen this valid signatures. Then I just use the succinct proof to prove that I saw this valid signatures. I just succinct because the succinctness promises the shortness of the signature here.
Why would you care about zero knowledge?
We don't talk about zero knowledge for now. Yeah. Zero knowledge is another property. Today we just focus on succinctness. Yeah. Okay, so this is one specific application of the succinct proofs. Yeah. Okay, so then next part we are going to talk about polynomial interactive proofs. Okay, so this is a very specific way how to achieve the succinct proof. So in many cases, people just compile the provers into polynomials. So actually, this is a very important topic in complexity theory, which is called PCPs. So basically, how to compress the proofs. So I'm not going to tell you how to compile them together, but I directly just talk about the polynomial. So imagine there's a black magic that converts the proofs into polynomial. So now we just focus on the polynomial. I'm going to skip the black magic for now. So what are the interactive PIOP, polynomial interactive oracle proof? So I'm just going to talk about a very easy, very simple instance of the PIOP, which is called sum-check protocol. Sum-check protocol was invented by complexity theorists to prove two computational complexity classes are equal. So people introduced this thing to prove IP is equal to P space, meaning for every computational problem in P space, you can use the interactive proof for it. So this is a very complexity theory oriented. Okay, so this is some background. So now let's talk about what are some check protocols. So given any fixed field, so we have a field, so we just play with a field, and then the prover has a polynomial g, so it has v variables. You can imagine this g is multilinear for now. So for simplicity, just imagine you have a multilinear polynomial, and then you want to convince the verifier that the summation. So this is a summation over the cubes. Boolean cubes, summation bi is summation of either 0 or 1. The summation of this polynomial is equal to h. So I want to convince the verifier that. Okay, so the verifier does not have any knowledge of g. So actually, if you go back to the previous succinct proof, you can imagine that g is the witness. G is the witness, and so basically we compile the witness into a polynomial g. Okay, so then the prover and the verifier engage in multi-round of communication. So we start to communicate. Okay, so in the beginning, okay, imagine the scenario is in the beginning verifier knows nothing, and then the prover knows the polynomial g. So they started communication. And in the last step, the verifier has the power to make a single query to g. So means you can query some. You can choose some v1, v2 up to, sorry, you can choose some r1 up to rv, right? And then you query g, then you get the correct answer of this query. So imagine that there's no way to cheat right in this step. So you just then you decide, then the verifier decide to accept or not.
If G is supposed to be the witness,
yes.
Why is the verifier only making a single query to it? Why is the verifier only making a single query to it? Like, why can't they just?
Yeah, because you have too many queries, then this is no longer succinct.
I see.
Yeah. So we want to make it succinct.
Like
Yeah, if you can query many, yeah. Actually, actually it can be relaxed to several queries, a few number of, as long as the queries don't that much, so you always succeed. But a single query just make it simple right here. Yeah, this is a very good question. Okay, any questions so far about this setting?
I guess H is public.
H, in many cases you can just imagine H is 0. So because you can just imagine H is 0. So because in many cases, whenever so this is because how we compile the proof the statement. Anyway, so H is 0. Any questions? Okay, so then how could we make this some check protocol? How to convince the verifier this is true? Okay. Okay, so actually, so the sum check protocol is very smart. Okay, so in the beginning is that the prover sent H, imagine 0 for now. Okay, so then the prover first sent, this is a polynomial G1, which is equal to summation, this is B, B2, B3, anyway, so summation for the B2, all for the B2 and BV are due under the summation, but the X, now we release X as a variable. Right, so because imagine that originally G has V variables, right? And the provers first send the to the summation of the B2 and the BV, and now this is only the first variable is still alive. So basically, this if the original G is multilinear, so then this is a degree 1 univariable polynomial, right? So basically, this it has degree 1 univariate. Okay, so then the verifier check whether G1 0 plus G1 1 is equal to H. Right. So if the prover is honest, so then this must be true, right? Yeah. Okay. So then check it. If this is not equal, then the verifier is going to reject. So you cheated. And then if they're equal, so then let's move on to the next step. So what is the next step? The prover, the verifier randomly sample R1. This random sample R1 over this field F. Okay, random sample R1, just uniformly random, public coin. Okay. So after sending this R1, the prover and the verifier fix X1 to be R1. Okay, so now the prover sends the next message. Now this is summation for B3, B4, and BV, but we fix R1. Okay, so then we are going to check whether G20 plus G21 is equal to G1 R1, right? Yeah, if this is honest, then this is still true. This is the issue. And then send another random seed R2. Keep going until they have communicated V minus R rounds. And in the final step, the verifier randomly sample RV. Random sample RV and query this G. Query G R1 R2 RV. And then you just check whether GRV, so GV minus 1 is the last polynomial received from the prover, right? So it keep going. So GRV is equal to the is equal to GR1 R2 RV. Okay, so this is soundtrack protocol. So in each round, we eliminate one variable. Okay. So what is the communication cost of this soundtrack protocol? Yeah, or the V number of ring elements, field elements, right? So it is just all the V has V. So recall that the polynomial G could have size 2 to the V because this is a multilinear variable. So the number of coefficients to be 2 to the V. So actually it can compile a witness of size 2 to the V. So meaning the V is usually the logarithmetic of the witness size. So this is how we compile it. So basically the proof size is polylog order of V. Yeah. So this is what we desire. And also this is a public coin. Because in each round we just send a random.
And when you say public coin, you see, is the point that somehow in a bad verifier could choose the R1 through RB in a way that undermines it?
Sorry, the verifier or
What is the, you keep saying public coins.
Yes, yes.
Is that because a verifier that if you weren't using, what does it mean to use public coins? If you weren't using public coins, the verifier could do something bad?
Actually, the reason is that because we want to apply fiat Shamir. So I actually did, I sort of have for a minute here, the public coin. So we can use the fiat Shamir to transform public coin into a non-interactive proof. Non-interactive proof is people wanted. Yeah. Yeah.
So public coins means that there's some source of randomness.
Yeah, we just need the randomness.
And the verifier extracts those bits
yes.
at the time that they're needed.
Yes.
And at the time that they're needed, they're not known by before they're needed, those bits are not known to the prover. Yeah.
Because just the purely randomness, that we can use sometimes why fiat Shamir works is that you just use cryptography hash function to extract the randomness. Yeah. Okay, so this is why we want a public coin. Okay, so then what is the soundness of this soundtrack protocol? Because we want the completeness is clear, right? So because whenever the prover always send the correct thing, then the verifier will accept it eventually. So the completeness is good. So what is the soundness? Soundness means if summation of G is not equal to H, so how could the verifier identify it? Right? Okay, so for simplicity, I just talk about the last step. The last step is that if GV minus 1 is not honest, if GV minus 1 is not honest, meaning this is not the correct answer, right? How would the verifier detect it? The reason is actually a very fundamental theorem in algebra, which is called Schwarz-Zippel. So means even though we have a degree D polynomial, and then it has only D roots. So I assume everybody knows it. So let's imagine if GV minus 1x is not equal to G1 up to GV minus 1. So it means this polynomial minus this polynomial is not a zero polynomial, right? So then the verifier in the last step of the verifier just randomly sample RV to replace this RV. So yeah. So then as long as the RV is not a root of this, the minus of these two, we can identify it, right? So basically since this is multilinear, then the degree is 1. So then the probability, the accept is alpha bounded by 2 minus f. So because we can choose the size of f to be super polynomial, but it's okay, right? So because it's only the dependency on f is just the logarithmic of f. So we can choose the f to be super polynomial, so then it is okay. So with high probability, the verifier can accept it.
Why 2 over f rather than 1 over f?
2 roots. Anyway, it doesn't matter. So because, okay, yeah, you're correct. Degree 1 has only 1 root. Yeah. I don't know what I thought when I was making these slides. But anyway, constant. Yeah. Okay, so this is a check. Okay, so then we are going to talk about the second half of this talk is about the sum check over polynomial. Yeah.
If you go back to the communication, so this assumes that the polynomial can be communicated with order of log f. Like for example, multilinear.
Yes.
So let's say I have something more complicated than multilinear.
Yeah, but it's still okay. If multilinear, then the degree is, let's say degree d, then you probably need to multiply d. Yeah, this is a very good catch. Yeah, thanks for this question. Okay.
But then, if you make f super polynomial,
yes,
then it will no more be, yes, I guess in terms of definition, you'll still be succinct, but practically you will not be succinct, right?
The succinct is okay because the size of f is super polynomial, but the bits of this f is log. Imagine that you work with a really large field. You already work with a binary representation of it. It's just a logarithmic of the field size. So this is okay. Yeah. Second, because the dependency is log f. This is very important. Yeah. Okay. So then this is what the polynomial sum check protocol, which is very useful in many applications. Okay, so the second half we are talking about sum check over polynomial rings. Okay, so then why we need polynomial rings? Actually, one of the very important motivation is that we want to study lattice-based cryptography. Yeah. So what a lattice-based cryptography is that so. Why we need to study lattice-based cryptography? One of the motivation is that lattice-based cryptography is a strong candidate for building post-quantum secure crypto systems, because this is also the agency such as NIST, they're trying to push this direction. Is that we want to transfer our current cryptography system from the group-based into the lattice-based, because group-based is no longer quantum secure. Shor algorithm or something like that can break the group-based crypto system. So then they want to move it to into a post-quantum secure thing. And the lattice-based is a very strong candidate for a post-quantum secure crypto system. For example, NIST. Do you have a question?
Okay, I was just wondering, when you say the subject or polynomial ring, so now you will want the point at which you will evaluate to be
also polynomial rings. Yes, exactly. But it's no longer. But now all of the coefficients are polynomial rings, and from rings no longer field. This is what we're talking about. Polynomial rings.
The point at which you evaluate.
They're polynomial over rings. Yeah, sorry. Yeah, you can first imagine this is a rings, because the original f is a field. Now the case is now we are moved to a ring, but it is a specifically interesting polynomial ring. Okay, so these are two different polynomial rings. So this polynomial is a polynomial ring. Okay, so lattice, so basically lattice-based cryptography involves computation of polynomial rings have this form. So this is the computation of the lattice. Computation of lattice is usually based on computation over these rings. This ring, this is a ZQ is a this is a ZQ. I mean integers modulo Q, and this is ZQX and modulo X to the n plus 1. So this is a polynomial ring, and n is usually a power of 2. Okay, Okay, so Q is an integer. Any integer would be fine. So, okay, so then if you want to prove the succinct proofs of a lattice-based signatures, then it requires arithmetic computation over polynomial rings. Right? So if you want to have a succinct proof for lattice-based protocols, so imagine that we gave an example such as the aggregated signature, for example, right? So if the aggregated signature, I mean, if the basic building block of the signatures were lattice-based, so they are computation over polynomial rings. So now you want to prove the language of polynomial rings. So this is the situation. So how could we? Now the question is, how could we prove the polynomial succinct proof for polynomial rings? Okay, so the first try is that we can still consider the soundcheck protocols, right? So we just mimic the previous soundcheck protocols over polynomial rings, such as now the situation is that now we still have f. Imagine that is ZP for simplicity, and now we have a ring is fx divided by x into 1. And then now the polynomial is from R to the V to R, and we want to convince this is true, right? So everything is the same. Okay, so yeah, okay, it looks a very intuitive approach, but do you see what is the problem with this?
Yeah, I mean, you don't have this unique root. I mean, the number of roots.
Yeah, exactly.
Is not bounded the same.
Yes, exactly. This is the problem. So we now in this polynomial ring, we do not have an upper bound of the number of roots of degree D polynomial. Even for this thing is that even for let's consider a very simple polynomial such as z times 1 minus z is equal to 0. In any field, you probably know this, the roots it has only 2 roots, 0 and 1, right? In field, but over the polynomial rings, let's say just give a specific for example. So then you have many roots such as 0, 1, and this number. And so this number, I use alternative colors. I mean, there are different roots. Actually, there are a huge number of roots. There could be 16 roots. 16 is 2 to the 4. Yeah, 16 roots. Yeah. Why there are so many roots? It is because this number minus 1 times 1 minus this number could be a power multiplication multiple of x to the 4 plus 1. So because this number multiple, 1 minus this is equal to a polynomial times x to the 4 plus 1. So it will be, the quotient will make it to be 0. Yeah, this is the major problem if we want to apply the soundcheck protocol over this the polynomial rings. Okay, so then actually because the Schwarz-Zippel lemma does not hold. Okay, so how could we do that? Okay, so actually our solution actually is very straightforward. Yeah, it sounds straightforward, but it still needs some tricks. But I'm going to hide the tricks today. So let's consider this question: how many number of the roots over of this polynomial over this ring? Notice the difference is that without the quotient. What is the number of the ring? Actually, you can prove there are only 2 roots again. So because we eliminated the quotient. Okay, So now actually we saw this is the lifted the ring. So we lifted the statement from the original. We lifted the polynomial from the previous polynomial ring into this ring. So we lifted it. So of course we must be very careful about this transformation to preserve the soundness and the completeness. I'm not going to talk about the lifting today, but imagine we have a magic again to lift it in the large ring. So now we can probably go through the same check again. Question?
I guess so. You just mean like instead of like we're basically going to have like a reduction where we can say like some check will hold for this.
Yeah.
If it holds for.
Yes, exactly.
Okay.
Yeah. We have this reduction. Yeah, but I'm not going to talk about the reduction today. Yeah. Okay.
So it kind of means like if you have a root in this,
yeah,
you can leave this root to.
No, we can check. We have another check to rule out the invalid roots. So yeah. But this is some works I haven't prepared to present that part. Trust me, we have room to do that. Okay, we now have this lift. Okay, lifted to the larger ring. Okay, So yeah, we have a paper released, posted online, so you can check the paper. Okay, so but for now, let's trust me, we have this lift technique, and now we have the larger ring. So now we can just go through the original process again. Okay, so we have this field. Now the situation we have a polynomial over this field, right? Into this field. Okay. Sorry, ring from fx to the w to fx. Now this is still polynomial ring without a quotient. Okay, so we can just do the same thing as before. Okay, so we just do the same thing before. So it's just the sum check. Okay, so it sounds good, but yeah, but do you still see any potential issue right here? So yes, exactly. Yeah. You guys catch the problems immediately. Actually, so because original, imagine that the original elements is from this polynomial ring, right? So then the degree could be as large as n. So now if we lift into a larger ring, so then this degree is still could be as large as capital N. So the degree of the ring size itself is really large. So then what is the communication cost of this process? It becomes this number. You have n over here. So yeah, right? So the proof size now becomes v times log f times n.
If the polynomials is all are derived from that original smaller ring.
I know largely.
If not, then the number of elements is infinite. So
yeah,
there's no bound at all.
Yeah. But the transformation keeps. Let's say you have actually the original ring. My point is the original ring is not small because the capital N could be very large.
Yeah. But it's still at least finite.
Yeah, finite. Yeah.
In the other ring, in the lifted ring, you're This transformation preserve the degree. Okay.
Yeah, preserve the degree. Yeah, but my place is still large. Yeah. Okay. So so the proof size now becomes v times log f times n. Yeah. Question?
I'm just kind of curious. Do you only have to do like one sum check protocol in the lifted ring, or do you have to do like maybe like many?
Lifting process only one sum check.
Okay.
Yeah. Okay. So so the question is that the ring dimension n could be very large in lattice. Actually, in lattice, whenever n is getting larger, then you have a better compression ratio. So because in the lattice, people want to whenever n capital N is getting larger, then we have a larger polynomial ring. Then it can encode more information. Actually, so in many cases, such as for example FHE, fully homomorphic encryption, this is a very important application of lattice. So the n could be as large as 30,000. It's really large. And so, for example, in many cases, this could be as large as 1024 to the 10. So yeah, actually, so I just had a discussion with Peihan just a couple hour ago. Is that because in the SNARK, one application of the polynomial ring, one SNARK, in the existing approaches, people have to limit the size of the capital N because this reason. So, but do you see the trade-off? Because in the lattice side, you want a larger ring, but in the proof size, you want a small ring, right? So because there is something, incomparable. So whenever you have a lattice side, you have a larger ring, you have a better performance of the lattice itself. But if you want to prove it, if the n is getting larger, then the performance is getting worse. Yeah. So how to resolve it? Actually, this is a very simple observation in our paper again. Is that this is because we can lift the ring. Actually, the trick is very simple because we already lifted the ring. So we already lifted the ring. So the simple trick is the following: is that we just first send the verifier just randomly send alpha, randomly sample alpha in the beginning. Now we modify the sum check protocol. Is that in the beginning we first randomly sample alpha, and now the prover and the verifier replace all of this x by alpha. Just replace all of the x by alpha.
You're not changing the
Ring.
ring, it's just changing what gets communicated, I think.
Yeah, it's not the change. Yeah, it's changing the ring to F. Alpha is the element from F. Imagine you have a ring such like a summation of AI times x to the I. You just compress it to summation of AI times alpha to the I. Alpha to the I is still element from F.
I think what's confusing is that you say, you define the ring it's over in
Yeah.
terms of x, and then you say replace all x in G by alpha, but you don't mean replace it in the definition of ring. I think
Yes.
You just mean whenever
Yeah.
x is a variable in your protocol,
Yes.
you use alpha instead.
Yes.
That
Yes.
doesn't, it's not changing the, so
Yeah.
you see the confusion that
Yeah.
you're
Sorry.
using x in two different ways.
Yeah.
One to define the ring of polynomials.
Yeah.
And where x is a variable is just a formal thing.
Yeah.
And then here x you're talking about a variable in the middle of the
Yeah.
protocol. You might want to use a different variable.
Yeah, good suggestion. This is a very good suggestion. Okay, so let me try to explain it again. So here is that because this is the G, you can imagine that this is just the G as the summation of okay.
So it's just evaluation.
Just evaluation map, exactly. Yeah. Just evaluation map. Yeah. So we just one more step. Okay. So now we follow this protocol. Yeah. Just as a protocol over F.
You're gonna say something about why that sound?
Yes. Yeah. The sound is that because actually in high level way is that the sound because the capital N is much smaller than the F. So the soundness error we can prove actually is the degree of G degree in terms of X over the F. Actually, you can imagine this G as originally G was multilinear polynomial with V variables, right? So now you can imagine consider G just as V plus 1 variables. So actually, the point is right on. Okay, right here.
Yeah, or I can raise
Yeah.
this, you can see the screen.
Yeah. I can just write a small part.
Reach the the whiteboard is not raised after.
I think another solution is that I can. Okay. Okay. Actually, it is pretty.
You want me to not do that?
I think it's fine. So I just it'll be very quick. It'll be very quick. I almost finished my talk, so it'll just be very quick.
Yeah, just
Okay, just right here. I have a space.
Sorry. I just bring up one of the small ones.
no. I think like if that space is enough.
I think
right?
okay. This space.
Yes.
Okay, sure. Yeah, because G is equal to the G is we can consider G as x0, sorry, x and we okay y, and they're trying to use y1 yr. So original G is a polynomial over fx with these variables, right? So now we just identically consider this is as such this polynomial over f. This is the idea. So basically, the evaluation is that you just evaluate this polynomial over f. We just put the x itself as the variable of this polynomial.
So y1 to yr are coefficients.
Of degree 1, multilinear. If you just look at y1, this is multilinear. But x is just another variable. So the soundness for this variable. So you can imagine this is actually, if you put everything together, this is just a sound check protocol over f for this polynomial. One more variable. This is just the sound check for this polynomial over f. Yeah. So the soundness for x is capital N divided by the field size. Field size could be very large, right? So it can be super polynomial. N is still polynomial. So this is not a big problem.
size of a field because
The degree of x is
I have n.
yes for x.
This is yeah.
Yeah.
Um,
Yeah. Yeah.
Adding one more round.
Yeah, one more one. Yes. Yes, very beginning. So yeah. Now you can reduce the proof size again into sorry. You can reduce the proof size again into just like previously it was v round, right? And each round equals to capital bigger O log f. Now you have just one more round with the same.
so instead of sending a polynomial of x in
Yeah.
each round of that flow,
Yeah,
I just
because
send
alpha-
its value at the
Yes. Now you can save the n factor. So this is a big save.
So when you apply this evaluation map,
Yeah.
don't you need all the resulting because when you apply the evaluation map, when you're
Yeah.
going when you're going to get in some sense the summation of different potentially multilinear polynomials, right? Evaluated at alpha.
Yes. But the alpha is no longer multilinear. It is, but the degree is capital N.
But I guess my question is to get the sum of n over the field size, right? You
Yes.
use only one of those because one of those polynomials that appear in that summation of the evaluation map. Do you need only one of them to be non-zero?
Could you say again? Yeah, probably you can also talk it offline. So because we almost finished, you just have so we can talk it offline. I have plenty of time offline. Yeah. Okay. Here, yeah. So some quick summary and future works. So the summary is that in our paper we have a generic transform from PILP over polynomial rings like this into a PILP polynomial interactive field, or Galois rings sometimes. Why Galois rings? Because in the lattice sometimes this Q is not a prime number. This Q could be a power of 2. In many applications such as FHE, they like the Q to be a power of 2. But whenever Q is a power of 2, then F itself is not a field. Yeah, so we have to actually we have one more step for that cases. So we have to lift it to a Galois ring. Anyway, I'm not going to talk about it today. So this is how we resolve this issue. Okay, so some of the applications. So one application I have already mentioned is that how could we construct an efficient aggregate signature for lattice-based digital signatures, such as Falcon. Falcon is one of the protocol that's standardized by NIST for post-quantum secure. So basically, if we have efficient aggregate signature for Falcon, then we can, if you can efficient aggregate Falcon, then probably we can have efficient post-quantum secure aggregate signature. Yeah. And another thing is the verifiable FHE. FHE itself is a very important application for lattice, and is a very exciting area in cryptography as well. So the idea of FHE is like that. Imagine that everybody today is going to use cloud service, right? So for example, Amazon, AWS. So, but sometimes the client might have some concerns about the privacy of the data. So for example, if on AWS to compute something for you, you are submitted the data to the AWS. So probably some people will be concerned about it. So the idea is that the idea of FHE is that we first encrypt the data and send to AWS, and the AWS can do some magic computation over the encrypted data. And the AWS never knows any information about this thing, but they can do the computation and then return encrypted data as well. But the magical thing is that whenever the client can decrypt the output by the AWS, whenever it decrypted it will magically the same as the computation that you wanted. Okay, so this is FHE. So, but in this process, nobody can. In this process, because since you do not trust AWS, how could you know that AWS honestly executed what you want? So you need to verify. You need to prove, okay, I honestly executed your order. So this is verified by FHE. And also,
you have these question marks.
This is a potential
under applications.
Yeah.
Does that mean that you haven't
So-
figured out how?
So theoretically, we can figure out it, but question mark means I want to really get an efficient thing. So for example, so why we put a question mark here is that efficient, because the efficiency is something you never resolve it, right?
Yeah.
So how efficient it could be, we have to run implementation and then we'll
Maybe
see.
FXE is still not efficient
Yeah.
even without verification.
Yeah, I know. That's why I put the question mark
I
here.
see.
Yeah. Theoretically, of course, this can be solvable. Yeah. So of course, we wanted the practical solution. That's why I put the mark here. But for the first one, I think this is very doable. Yeah. That's it. Thank you for attending. Yeah.
So I have a question, like,
Yeah.
for this alpha thing, I feel we suddenly switched gear, went very fast on this line.
Yeah.
So what's suppose I generate a random element in the field in each round of that protocol?
You just one run at the beginning.
Yeah, but that's fine too. Like if I want to generate a
Different
so
alpha.
can I think of it as when I try to verify if you lied in the yeah, you're splitting this polynomial.
Yes.
You're fixing it one by one.
Yes,
So I guess
yeah.
instead of yeah, so I'm just struggling a little bit on this slide, which I feel is
Yeah, I think so. The high level solution is that we just imagine this G polynomial G over this field, this ring as a G like this, Gx to the y1 over F.
yeah, I don't care.
Okay.
Yeah, sorry.
Okay.
I was just saying, maybe it would be best to look it as the commutative diagram where
Yeah.
you have fx to v map to fx. Now, by using the evaluation map, you lift from fx to the v to fv.
Let me try. Okay, so the G, what is the form of G? Yeah, I think I can give a very quick writing here. All right. So G has the form because since G is in this F, x to the v, right? So if you write it, this is equal to the summation of summation of A. A is something in this field. A times x tilde something I, and some of the s or something like that. Something like that. Y1, yeah, Y1, some of them here, some of them not here, right? Yeah. Y or whatever. So you can, this is exactly, you can rewrite it. You can imagine this is just as the polynomial over f to the v plus 1. Yeah. This is polynomial. Yeah.
So
this is just.
If in the very beginning you.
Yeah, I should mention this thing, right?
What you did for
Yeah.
all the later
yeah.
y's, but you
Yeah.
do it for x first.
Yes,
very
yes,
first round. And
yes.
As long as you don't get super unlucky that you hit the root
Yes.
of this, then the rest of the protocol would
Yeah.
carry out.
Yeah. This is just the degree n polynomial with v plus 1 variables over f. Yeah. Yeah.
And you can know the intuition why the sum check for this polynomial is useful, or like how to use
How to use what? The
sum check,
for this
sum check for the polynomial.
for which for original for this?
It's
Yeah.
like summation over all b.
Okay. Why we need a summation for all
why
b?
do we need-
Okay. So you can imagine that each b1 up to bv encodes a restriction, because you want to prove R1CS or whatever, you prove some system, you have many constraints. You have a 3 set, right? So you have many constraints. Each constraint can be encoded by an assignment of b1 up to bv. Yeah. So basically, if you have a so we encode it if so this encoding could be probably I don't have time to discuss it today because
But I suppose every language can be.
Yeah. So you can first compile each MPU to R1CS. So each assignment of these are, so whenever each assignment of B up to BV corresponding to a restriction, a constraint, sorry, constraint or constraint. Yeah.
So for this is easy to capture R1CS.
Yes, polynomial. Yeah.
Right, let's thank Jiapeng again.
Thanks. Thanks for coming.
We'll be around to answer your questions.
Yeah. Thanks.
So what's the bottleneck of